Base R graphics. Base R provides a simple and straightforward system for creating static graphics. The plot function is one of the most basic and versatile plotting functions in R. It automatically selects a suitable plotting method based on the input data. The code snippet above creates a basic scatter plot with x being the numeric vector for x-axis values and y as numeric vector for y-axis values. The main argument adds a title to the graph. xlab and ylab label the x-axis and y-axis respectively. The col parameter sets the color of the points to blue. ggplot2. ggplot2 is a popular R package for creating complex and aesthetically pleasing graphics. It is based on the grammar of graphics, a framework for constructing plots by specifying layers, scales, and coordinate systems. Here, we'll create a simple scatter plot. First, we load the ggplot2 package. Then we create a data frame df with two variables x and y. Variable y is the square of x. Next, we call ggplot and specify the data frame and es. To define aesthetics mappings, here x and y axes. Finally, we add geom_point to plot points, resulting in a scatter plot. Plot customization. In Base R, you can customize plots extensively. Below is an example of how to customize a scatter plot, changing the main title, axis labels, point type, and color. The plot function creates a scatter plot of x and y values. The main parameter sets the plot title. xlab and ylab set x and y axis labels respectively. pch specifies the point type, with 19 being a solid circle. col sets the color of the points. Interactive graphics with Shiny and Plotly. Shiny is an R package that makes it easy to build interactive web applications straight from R. Plotly is a plotting ecosystem that includes a JavaScript library for creating interactive graphs. The Plotly R package provides a seamless interface to the JavaScript library directly from R. Interactive graphics allow users to manipulate the visuals and drill down into the data for better insights. We will not be including any specific code in this explanation, as it is an introduction to the topic. Shiny applications have two main parts: a user interface script, UI.R, and a server script, server.R. The UI.R file defines the layout and appearance of the app, whereas the server.R file contains the instructions to build the app's reactive elements and the data processing. Plotly graphs are interactive by default and can be easily integrated into Shiny applications to make the visual representations more dynamic and engaging. Creating reports with R Markdown. R Markdown is an authoring format that enables easy creation of dynamic documents, presentations, and reports from R. It combines the core syntax of Markdown, an easy-to-write plain text format, with embedded R code chunks that are run so their output can be included in the final document. R Markdown documents are fully reproducible and support dozens of static and dynamic output formats. The code provided is a basic example of an R Markdown document. The YAML header at the top specifies the title and the output format. The text that follows is written in Markdown, a lightweight markup language. The code chunks, surrounded by R, contain R code that will be executed when the document is knit. The summary cars command outputs a summary of the cars dataset, which is provided by R. When you knit this R Markdown file, an HTML document will be generated with the text content and the results of the embedded R code. Descriptive Statistics. Descriptive statistics summarize and describe the features of a dataset. This generally involves measures of central tendency, like mean, median, and mode, and measures of variability, like standard deviation and variance. In R, we can use the summary function and other descriptive functions to understand the distribution of the data. The code begins by creating a numeric vector data with sample values. The summary function then provides a 6-number summary: minimum, first quartile, median, mean, third quartile, and maximum. We then get the mean and median of the data using mean data and median data. Finally, SD data computes the standard deviation, which measures the amount of variation from the average. Probability distributions. In statistics, probability distributions describe the likelihood of outcomes for random variables. The distribution can be discrete, where outcomes have exact probabilities, or continuous, with probabilities described over intervals. R provides functions to work with different probability distributions. For example, norm, pnorm, and qnorm deal with the normal distribution to calculate density, cumulative probability, and quantiles, respectively. This R code calculates the cumulative probability up to a z-score of 1.96 for a standard normal distribution, mean of 0, and standard deviation of 1. It uses the norm function, which takes a value, the mean, and standard deviation of the normal distribution, and a logical value for lower dot tail. When lower dot tail is true, it returns the probability of obtaining a value less than or equal to the specified z-score. In this case, it calculates the area under the normal curve to the left of z-score 1.96. Hypothesis testing. Hypothesis testing in R involves making an assumption about a population parameter and then testing whether this assumption is likely to be true or false based on sample data. A common test is the t-test, which can be used to compare the means of two groups or a group against a known value. The t.test function in R performs a t-test on a dataset. In this example, data variable represents the sample data we are testing, and the mu parameter is set to the expected mean from the null hypothesis. The function will return an output, including a t-value, degrees of freedom, p-value, confidence interval, and the sample mean, which can be used to determine if there is enough evidence to reject the null hypothesis at a chosen significance level. Linear regression and diagnostics. Linear regression is a basic and commonly used type of predictive analysis which assumes a linear relationship between the dependent variable, which is the variable we are trying to predict, and one or more independent variables, which are the inputs we think are influencing our dependent variable. The goal is to model this linear relationship by fitting a line in 2D space or a hyperplane in multi-dimensional space to the observed data which best represents this relationship. The LM function in R is used to fit linear models. It takes a formula and data as arguments. The formula specifies the dependent variable followed by the h symbol and the independent variables. You can add multiple independent variables separated by the plus sign. After fitting the model with LM, calling the summary function on the fitted model object provides you with the regression coefficients, standard errors, R-squared value, and other statistical measures to understand the quality of the regression. ANOVA. ANOVA, which stands for Analysis of Variance, is a statistical technique used to compare means across multiple groups and determine if any of those means are significantly different from each other. It is particularly useful when dealing with 3 or more groups. The base R function for conducting an ANOVA is AOV. Here's how you can use it. In this code, AOV is used to perform the ANOVA test on a dataset datet, where response is the dependent variable and group is the independent variable factor. The brace symbol indicates that we are modeling the response as a function of the group. The result is assigned to fit. The summary function is then used to get a detailed summary of the ANOVA analysis, including the F statistic and p-value, which you can use to assess statistical significance. Time series analysis. Time series analysis involves statistical techniques used to model and analyze time-ordered data points. Such data often arise when monitoring industrial processes, tracking corporate business metrics, observing financial market fluctuations, or environmental changes over a period of time. In R, TS function is commonly used to create a time series object. This line of code creates a time series object from data, assuming it represents monthly observations, starting from January 2021 to December 2021. The start parameter defines the starting time point, the end parameter defines the ending time point, and the frequency parameter indicates the number of observations per time unit, 12 for monthly data. Data table package. The data.table package in R provides an enhanced version of data frames with syntax that allows for more efficient data manipulation and retrieval. It is particularly useful for large datasets and includes features for aggregation, updating, and joining tables. This code snippet loads the data.table library, then creates an example data table object named DT. It has three columns x, y, and v. The x column is filled with repeating values a, b, and c. The y column has a simple pattern, and the v column is filled with consecutive numbers from 1 to 9. Dplyr tricks and tips. The pipe operator %, provided by the magritter package and popularized by Dplyr, allows you to chain together functions in a way that is more readable and concise. In this example, the dataset data is first filtered to only include rows where score is greater than 50, and then it is passed to the select function, which keeps only the columns name and score. The %, operator passes the result of each step to the next. Handling missing data. In R, missing values are represented by the symbol NA. To identify missing data in a vector or data frame, the function is.NA is commonly used. This function returns a logical vector indicating whether each element is NA. In the given code, we create a vector data vector containing some NA values to represent missing data. We then apply the is.NA function to this vector. The function returns a Boolean vector, is.NA vector, where each element is true if the corresponding element in data vector is NA and false otherwise. We print is.NA vector to see the result. Date and string manipulation. In R, date manipulation involves converting strings to date objects, formatting dates, extracting components of a date, and performing operations on dates. The lubridate package greatly simplifies these tasks. The library lubridate call loads the package needed for date manipulation. Date 1 is initialized as a date object representing April 1, 2023. Year, month, and day functions extract the corresponding components. Date 2 is created by adding 10 days to date 1. Efficient operations with purrr. The purrr package in R is designed to make operations on lists and vectors more efficient and user-friendly. The package provides a set of functional programming tools for iterating over elements, performing transformations, and simplifying results. One of the key functions in purrr is map, which applies a function to each element of a list or vector. In this code snippet, library purrr loads the purrr package. The map function applies a function to each element of the input, which in this case is the numbers from 1 to 5. The breaks.x2 is a formula shorthand for a lambda function in R, where .x represents each element of the input. The map function then doubles each number. The result is a list where each element is twice its original value. S3 and S4 classes. S3 is R's simplest and most common system for object-oriented programming. It allows for polymorphism and encapsulation by enabling methods to behave differently depending on the class of their input. There is no formal class definition. Instead, classes are assigned to objects by setting a class attribute. The code defines a generic function with the use of use method, which dispatches a function based on the class of the argument x. We then define a default method for any object that doesn't match a specific class method, and a method specific to my class. We create an S3 object, obj of class myClass, and finally call the generic function with obj, which will use the myClass method. Reference classes, R6. R6 is a more modern way of implementing reference semantics in R. Unlike S3 or S4 methods, R6 objects are mutable and have reference semantics, meaning changes to one instance of an object affect all references to it. In this code, we define an R6 class named person with two public properties, name and age, and two methods, initialize and celebrate birthday. The initialize method sets the initial values for name and age when a new object is created. Celebrate birthday increments the person's age and prints a birthday message. We create a new instance, John, and celebrate his birthday, demonstrating how methods can modify the properties of an R6 object in place. Methods and generic functions. In R, a generic function is a function that can behave differently depending on the class of its input. Methods are functions that define the behavior of a generic function for a specific class type. First, setGeneric creates a generic function describe. Then, setMethod defines what happens when describe is called with a numeric or factor object. For numeric, it returns the mean. For factor, it returns a frequency table. When describe is called with a numeric vector, it invokes the numeric method and computes the mean. When called with a factor, it invokes the factor method and generates a table. Method dispatch. Method dispatch in R refers to the process by which R decides which method to use when a function is called on an object. This is part of the polymorphism concept, where different classes can have methods with the same name but different behaviors. In R, the most common object systems are S3 and S4, each with its own dispatch mechanism. In the provided code, we define a generic print method, print.generic, for non-specific objects, and a specialized method, print.myClass, for objects of the S4 class, myClass. When we create an object of myClass and call the print function on it, R uses S4 method dispatch to determine that the print.myClass method should be called because the object has class myClass. Thus, the custom message about myCustomClass is printed, along with the value stored in the value slot of the object. Prototypes. In R, prototype refers to a default object of a class, which outlines the structure and storage mode for the attributes of objects in that class. Prototypes are used in the S3 and more formally in the S4 object-oriented systems. The setClass function is used to define a new S4 class called person. It has two slots, name and age, which are character and numeric data types, respectively. The prototype for this class specifies default values. For name, it is unknown, and for age, it is NA, not available. Any new object of class person that does not explicitly set these slots will inherit these default values. Efficient programming, memory and speed considerations. Efficient programming regarding memory and speed involves writing R code that is optimized to be fast and to use the minimal amount of memory possible. This can be crucial when working with large datasets or in time-sensitive scenarios. In the code, we use the prowess package to measure the size of our objects in memory. We generate a numeric vector x with 100,000 entries using rnorm. We then use system.time to find out how long it takes to perform a simple computation, doubling each number in the vector. We store the size of the object x using object size to understand how much memory it consumes. Parallel computation. Parallel computation in R allows for the execution of code on multiple processor cores at the same time, reducing the computational time for tasks that can be performed in parallel. R has several packages that enable parallel computation, including parallel, forh, and future, among others. The parallel package provides support for parallel execution by means of multi-core processing and cluster computing. The code starts by loading the parallel package. The detect cores function is called to determine the number of available processor cores. Then mclapply is used to apply a function, in this case the square root, to each element of the vector from 1 to 4. This is done in parallel using two cores, mc.cores equals 2. Integration with other languages, C++, Python. RCPP is a widely used package in R that makes it easy to integrate C++ code. It provides a seamless interface between R and C++, allowing for both improved performance and access to C++ libraries. Below is an example of how to use RCP to create a simple C++ function that can be called from R. In the code provided, RCP is loaded in R using the library RCP function. Next, a simple C++ function to add two integers is defined. The comment RCP export before the function tells RCP to make this function available to R. Below the C++ code, an R snippet is included within store RR, demonstrating how to call the add function from R and print the result. Bioconductor for genomic data analysis. Bioconductor is an open-source project providing tools for the analysis and comprehension of high-throughput genomic data. It uses the R statistical programming language and is highly interoperable with various bioinformatics tools. The provided code shows how to set up Bioconductor and how to install a specific package. The first part runs a script to install Bioconductor, and the second part uses the bioc function to install the genomic features package, commonly used to represent and manipulate genomic features and their associated annotations. Creating R packages. Creating an R package allows you to bundle together code, data, documentation, and tests, facilitating easy sharing and reuse. In this section, we'll go through the basic steps of creating a simple R package. The command from the DevTools package initializes a new R package directory structure under the name myPackage. It automatically generates folders and files according to the standard conventions for R packages, including description and namespace files, and R and man directories. Supervised learning algorithms. Linear regression is one of the simplest supervised machine learning algorithms, which models the relationship between a dependent variable and one or more independent variables using a linear equation. In R, you can use the LM function to perform linear regression. This code snippet demonstrates how to create a linear regression model. The LM function is used where dependent is the dependent variable and independent is the independent variable from the dataset myData. After fitting the model, Summary Model provides detailed information about the model coefficients, statistical tests, and performance metrics. Unsupervised learning algorithms. K-means is a popular clustering algorithm in unsupervised machine learning. It aims to partition observations into K clusters in which each observation belongs to the cluster with the nearest mean. The algorithm achieves this by creating K centroids, one for each cluster, and then assigning data points to the nearest cluster while keeping the centroids as small as possible. This R code snippet demonstrates how to use the built-in k-means function to perform k-means clustering on the iris dataset. The function requires numerical data, so iris14 is used to select only the first 4 columns of the iris dataset, excluding the species label. The algorithm is set to partition the data into 3 clusters, and the nStart parameter ensures that multiple initial configurations are used to avoid local optima. After the algorithm has run, the results, including cluster assignments and centroids, are printed. Cross-validation and Bootstrap. Cross-validation is a technique for assessing how a predictive model will generalize to an independent dataset. A common form of cross-validation is k-fold cross-validation, where the dataset is divided into k smaller sets. The model is trained on k1 of those sets and validated on the remaining part. The code first loads the caret library, which is commonly used in R for creating predictive models. A seed is set for reproducibility. Create folds is used to create 5 folds of the dataset without overlap, ensuring that each instance is in a validation set exactly once. Train control is set with cross-validation CV method and 5 iterations for the number of folds. The train function from the caret package then fits a linear discriminant analysis LDA model using the defined cross-validation settings. Model selection and tuning. In the realm of machine learning, model selection involves choosing the appropriate model from a set of potential models. The best model is typically identified through comparison of performance metrics across models. Part of model selection may also involve feature selection, where the aim is to identify which features, variables, provide the most predictive power for the model. Model selection is essential since different models behave differently depending on the type and complexity of the data. Selecting the most appropriate model can lead to better performance when making predictions on new data. It's important to find a balance between bias and variance, as well as to consider the interpretability of the model, computational efficiency, and complexity. Techniques for model selection include cross-validation, where the dataset is split into training and test sets to estimate the performance of the model on new data. Metrics such as accuracy, precision, recall, AUC, or mean squared error are used to compare models. Ensemble methods. Ensemble methods involve combining multiple machine learning models to improve predictive performance compared to single models. They can reduce overfitting, improve generalization, and lead to better predictive accuracy. There are different types of ensemble methods, including bagging, boosting, and stacking. In the provided R code, we're using the caret and random forest packages to apply a random forest model, a popular bagging ensemble method, to the iris dataset. After loading necessary libraries and data, we create a partition to split the data into training and test sets using create data partition. We then train a random forest model on the training set and make predictions on the test set. The performance of the model is evaluated using a confusion matrix, which compares the predicted species of flowers to the actual species from the test data. Machine learning pipelines. A machine learning pipeline is a way to codify and automate the process of transforming raw data into actionable insights. In R, you can use the caret package to streamline the creation of predictive models and their pre-processing requirements. Pipelines help ensure that the same steps are applied to both training and new data consistently. In this code, we first load the caret package. Then, we create a preproc object that specifies the pre-processing steps for our data, centering and scaling in this case. We then use the predict function to apply these pre-processing steps to the training data. Finally, we train a random forest model with the pre-processed training data using the train function from caret. The independent variables are denoted by the dot, and the dependent variable is target. Working with caret, MLR, and tidymodels. The caret package in R stands for Classification and Regression Training. It is a comprehensive framework for building machine learning models in R. It simplifies the process of data splitting, pre-processing, feature selection, model tuning using resampling, and variable importance estimation, among other things. This code snippet demonstrates the utilization of caret to train a random forest model. We load the caret package, prepare the iris dataset by splitting it into training and test sets, define cross-validation with 10 folds CV for tuning the model, train the model using the train function with the species as the response variable, and then evaluate the model using the held-out test data. The performance of the model is assessed with a confusion matrix.